Good morning. So today I want to finish what I want to say about inflation. That's maybe too loud. So just a repetition. So you define inflation as an era where the Hubble co-moving radius was rapidly decreasing at the, before the radiation era started. And we have seen that this condition sort of leads to two conditions, which are characterized in terms of these parameters epsilon and eta. So the first condition tells you that really this is satisfied, that I have rapidly shrinking Hubble sphere, and you can write it in terms of the Hubble parameter dot over h squared, and this must be much smaller than 1. And then you have another parameter eta, which tells you that my expansion lasts sufficiently long so that I can get those 40 or 60 e-folds. And so that's the second condition. We have also seen that to get accelerated universe, accelerated expansion, you need some weird equation of state, namely that rho plus 3p must be smaller than 0, or that this w parameter must be smaller than 1 minus 1 over 3. So that tells you, so this condition violates a strong energy condition in general relativity. So it tells you that you are basically outside of the classical regime of GR. But yeah, so you can definitely do it. And so there are various models how you can model your inflation, and you will discuss many of them in your explorations. But let me just, we started discussing this holy grail of inflation, which is the single field slow roll model of inflation, where you just consider a scalar field with the standard kinetic term and some potential V, and then we will see today what are the conditions which you have to impose on this potential V so that you really can satisfy all these conditions here. So now we will be solving this thing respecting all the symmetries of the universe, so the homogeneity and isotropy. So and that limits that your scalar field can be function only of time and not space. So we are basically neglecting spatial fluctuations at this point. We will return to spatial fluctuations next week. But at this point, just we have phi of t. And then the two independent equations you get for this model is really your Friedmann equation and the Klein-Gordon equation for the scalar field, if you want. So these are the two equations. By the way, I redefined my m Planck, so now I'm absorbing m pi, 8 pi into m Planck, just to simplify life a little bit. Okay, so these are the two equations, and so far this is just a scalar field, single scalar field, but there's no slow roll approximation. So slow roll approximation really comes from the fact that I want to satisfy these conditions. Okay, so this is just a scalar field theory so far. So now we want to impose this slow roll approximation. And so for that, you need to calculate what these parameters epsilon and eta are in this given theory. And you can do that. So basically you have to mess with these equations a little bit. So just differentiate the first one, plug the second one, and so on. So you can play with that on your spare time. And what you get is that this is equal to, well, that's my definition, but it's equal to 1/2 phi dot square divided by m Planck square h square. So if you play with these equations, this is what you find. And of course, this is nothing else than this thing describes my kinetic energy of the field. So it's rho kinetic. And this thing from my Hubble equation describes the total energy in the field, rho. So it's rho total. And the condition that, well, we have a condition that this must be much smaller than 1. So in other words, your kinetic energy in the field, well, you have inflation when the kinetic energy in the field is much smaller than the total energy, or if 1/2 phi dot square is much smaller than V. right? So this is my condition, which I'm getting from here. And so that's why it's called slow roll, because it means that the value of the field is changing only very, very slowly. So basically, well, the kinetic energy is much more than the potential energy. Okay. So now the second parameter, eta, well, it's epsilon dot over h epsilon. And so again, if you play with the equations, you find that this is equal to epsilon minus delta, where delta is minus phi double dot over h phi dot. Okay. So now you require that this guy is much smaller than 1, but you already know, so this is your condition in the absolute value, maybe. Some things may be negative. But you already know that epsilon is much smaller than 1. So in order this to be satisfied, delta also has to be much smaller than 1. Okay, so you have a condition that this parameter delta must be much smaller, and perhaps this is an absolute value. And that comes from the second condition. So under these two conditions, that the kinetic energy is much smaller than potential energy, and that this quantity here is much smaller than 1, you really get inflation. Okay. By the way, if this is true, then your energy density is 1/2 phi dot square plus v, and the pressure was 1/2 phi dot square minus v. So if phi dot square is much smaller than v, you get actually W equals to -1. So this thing actually implies, so from here you also know that W is actually -1, which of course satisfies the condition on my equation of state, right? So these two conditions are actually stronger than requiring that rho plus 3p is smaller than 0. That already implies that. So we satisfy all the conditions for inflation. And so we may look how these equations actually get satisfied in this approximation, and these are called slow roll equations. So you get slow roll equations. So in the first one, I just neglect the phi dot square. So the first one is just 3 m Planck square h square approximately equal to v. And in the second one, I see that phi double dot must be much smaller than h phi dot. Okay, so that means that in the second equation I can sort of delete phi double dot. So the second equation is just 3h phi dot plus v prime equals to 0. So how we can understand the second equation is, if you want, this is something like having a harmonic oscillator with the friction term, which is the middle term, right? So now we are saying that basically the friction term is huge, right? So you have, what is it, overdamped something, harmonic oscillator. So that's your slow roll equation and approximation. So now, these are our equations of motion for in the regime where I have inflation. It is also useful to rewrite these conditions, that epsilon is much more than 1, or this one and that one, using these equations as a conditions on this potential V. Okay, so for example, so why don't I give you the result first? So you introduce new parameters, epsilon V, which is actually nothing else than my parameter epsilon. And you can rewrite it in this form in terms of the potential V prime over V. And so my condition is that this is much smaller than 1. And then you can introduce another parameter, eta V, which depends again on this potential, which is epsilon plus delta. So epsilon is small, delta is small, so eta v must be also small. And that equals to m Planck square v double prime over v. And you all, again, want this to be smaller than 1 in the absolute value. So these are the conditions. So how I get these, it's very simple. You just play with these equations and with the definition of delta and other things. So let me just do the first one, and then you can do the second one if you want. So the first one you would get by squaring the equations which we have over there. So we have that v prime square is, well, over v square. Is from the second equation, it's 9 h square phi dot square, and then it's 9 m Planck to the 4 h4. Okay, so now you look at whatever is your definition of the parameter epsilon. And the definition of the parameter is epsilon is phi dot square or m Planck square a square. Okay, so this is equal to, so 9 cancels. Now I am curious whether this works. Right. I should be doing this thing, right? M Planck square over 2. So now I have to do 1/2 and then m Planck square here. And so you see that this is precisely should give you whatever the epsilon is written there. And so you see really, I just have to play with these slow roll equations and with my definition of epsilon and delta. And this is what it gives you, okay? So in some sense, these are just really conditions of how can I design my potential for the scalar field so that I have inflation, okay? Question? No? Okay. So another thing is how many e-folds I can get from this theory. So you know that I have to have this 40 to 60 e-folds. So let's calculate that number. So from the definition, you have logarithm of the comoving radius when the inflation was initiated, and then divided by when it finished. Okay. So now this is plugging the definition of this Hubble radius. So it's A star, H star, AI, HI. Okay. So now what is almost true, and you will discuss that in your tutorial, is that during the inflation, well, it's definitely true for slow roll inflation, is that H doesn't change too much. H is approximately constant. It comes from the fact that you have basically de Sitter expansion. In de Sitter, H is a constant. So this guy and that guy are basically the same, and you can cancel them. So this is logarithm of A star over AI. So now let's just rewrite it in a clever way. So this is equal to an integral from AI to A star of d log of A, definitely true. Now you can write d of log of A in terms of H and dt. So definition of H is A dot over A. So if so I'll just write it down. So this is Ti to T star H dt. Okay, so now this is, I can turn it to a potential phi I to a field H over phi dot d phi, just the chain rule. And now I can use one of my one of my slow roll equations, the second one, to change phi dot into v prime. Okay, so this is equal to minus 3 phi I phi star h square v prime d phi. And finally, you can eliminate h square in terms of v from the first equation in slow roll. So this is equal to 1 over m Planck square phi I phi star v over v prime d phi. So again, so now you have an expression for a number of e-folds, provided that you know how your potential looks like. Okay, so again, if you want, let's say, 40 to 60 e-folds, then you know how your theory should design your potential so that you get the right thing. So let me just draw a possible picture. So typical potential, which gives you the right inflation, looks like something like this. So you have V of phi and phi, and then you start with something and then go like this. So you have a slowly rolling field with some phi dot, which is relatively very small, until actually the slope becomes very, very steep. And if it becomes very steep, the kinetic energy becomes non-trivial, right? So basically the inflation ends somewhere here. So this is the end of inflation, meaning that so you start here on this hill, you move very, very slowly until this is steep, then inflation ends. Then your conditions are not satisfied anymore. And then you have, at this volley, you have sort of like oscillations of the scalar field. And this is precisely the time where you say there is a reheating. So this is where the kinetic energy of the scalar field is the largest one. But then you have to turn this energy, this kinetic energy, into heating up your standard model particles. And that's where the reheating occurs. So this is just a typical example of a potential which people discuss when they talk about single field slow roll inflation. Well, people looking into Higgs inflation, I don't know if there's probably some problem with it, but I don't know what the problem. Yes, exactly. So this thing, well, it doesn't have to be very long, but you know, this thing is very, but the decrease must be very slow, right? So that you really roll for a long time very slowly, right? So this is a model of how we can do inflation with single field. So let me just do the simplest possible example, which was a canonical example until recently, when it was sort of excluded by observation, but not really. So it's simplest example. And so you have V, it's just the simplest possible potential you can imagine, is just phi square potential, m square phi square. So if you have this potential, you can calculate what your epsilon V and eta V are. So if you want to construct this theory, of course, the theory is complete when you say what is M, and you know, yeah. So first thing you calculate is epsilon V, and you find that in this case it's actually equal to eta V, which is 2 m Planck square over phi square. So now requiring that this is much smaller than 1, it immediately tells you that the field, the value of the field when the inflation occurs, is super Planckian. Okay, so from here, you see that phi must be much bigger than m Planck. In other words, the value of the phi here, well, this is not phi, but this is phi, must be much bigger than m Planck. So is this a problem? Maybe. So you have super Planckian field. What would be really a problem is that if you have super Planckian densities, energy densities, because then you cannot trust anything. Then you cannot trust your quantum field theory. So if the energy density is too high, then you are screwed up. So additional condition is that energy density which is, in our case, is just the potential V, m square phi square, is much smaller than the Planckian density. Okay. So in other words, phi must be smaller than m Planck to the 4. Well, okay. Phi is smaller than m Planck square over m. So putting these two conditions together is that you have a window for your phi. M Planck is much smaller than phi, is much smaller than m Planck square over m. And that's your window for possible values of phi, which satisfy, where you can still trust your quantum field theory, but also you have the inflation. Okay. So if you calculate the number of e-folds from that formula, so you have v over v prime, well, v is this guy over v prime, and then you integrate over phi, then the result is proportional to phi square, as you can easily see. So n is something like 1 over 4 pi m Planck square phi initial square minus phi final square. So this is the number of e-folds which you get from this potential. So now let's just estimate what it gives us for the mass m. So we have this condition here. So let's make sure that this condition is satisfied. So let's take that phi is, let's say, 10 times m Planck. Okay, so consider phi I equals to 10 times m Planck, then this part is satisfied. Well, then phi at the end must satisfy this condition. Well, phi must satisfy all the time, but so in particular in initial and final, you have to satisfy this guy. So phi final is 1 over 10 m Planck square over m. And let's take typical value of the e-folds is equal to 60. So this guy is equal to 60. And so if you use this formula, use this estimate, use that estimate, it gives you a condition on m, right? So from here, you get that m Planck over m is something like 50. In other words, m is much smaller than m Planck. Okay, so this is called eta problem, and it's similar to, it's a hierarchy problem. So why the mass of my scalar field is it's not at the quantum scale, but it's actually much smaller than the quantum scale, quantum gravity scale. Okay, so this is a hierarchy problem. Which is similar to the problem why Higgs mass is much smaller than the Planck scale. But so what? So this is your theory. So you can perfectly do, at least at a theoretical level, you can do with the simplest possible potential, m square phi square, you get that mass of that scalar field must be much smaller than m Planck, but you can sort of get all the physics right. So now this phi square potential is sort of excluded by recent observations of Planck. So that's why people play with different potentials. So I refer you to Gong, who's playing with the linear potential in phi. But people play with phi to 3/2, phi 4, and so on. So you know, it's just phenomenological models in some sense, which are not, which are in, you know, consistent with the current observations, and you can still do with this very, very simple theory of inflation, and you solve so many puzzles by just, you know, putting this scalar field, basically. But, you know, even more beautiful, and we will discuss that next week, is that inflation not only gives you the solution to all these puzzles, but it also gives you the right inhomogeneities once you take fluctuations into account, which can give rise to the right structure growth in our universe. So that actually the tiny quantum fluctuations of this field actually produce you seeds of what is going to be a galaxy later on. Okay, and so that is consistent with the observations. So inflation very, very powerful, and the theory can be as simple as this thing.
So these perturbations are perturbations of phi, or are they
yeah, quantum fluctuations of phi.
Don't people say that the structural formation is caused by dark matter? And so these perturbations could be blown up by inflation, or are you saying that?
You will see next week. But basically, the idea is that, you know, this field is fluctuating, and so it produces some inhomogeneities, and so these inhomogeneities are sort of like stretched out, and then of course, you know, matter content plays the role on how the structure formation goes, right? But the statement is that this gives you very nice initial conditions. These fluctuations give you very nice initial conditions, which are consistent with this kind of observation of what you see the large scale structure is in the universe. Okay, so that's, I would say, the most, you know, the most beautiful thing about inflation is that it gives you very nice initial conditions to think about. Okay, questions, other questions? Oh, very good. So that completes chapter 2. And so we are basically done with, I would say, like basic introduction to cosmology. So starting now on, we will discuss some little bit more advanced topics, like these inhomogeneities and stuff like that. But before we do that, I think we deserve another joke. But that joke actually needs some preparation. Okay, so the first step is that, I don't know, but maybe you know that Finns don't really like Russians. It's historically done. So Finns and Russians, they don't like each other. And of course, you know, Finns were oppressed by Russia, and then Finland expanded to Russia for some time in the past of this. So they don't like each other very much. So that's first preparation. So it's very politically incorrect joke. Okay. So second preparation is, I don't know if you know what a hand car is. Okay, so hand car, very important. So it's like a train, but it doesn't have an engine. You have to actually push it yourself. Okay, so it's a train. It goes on the rails, right? And then it has something which you have to push. So if you have a person here, then you push up and down, and there's another person perhaps here who has to push up and down, and then the hand car actually goes. Okay, and you have to push pretty hard if you want to get somewhere. Okay, so that's a preparation for the joke. So now you know what a hand car is. So imagine a Russian guy is lost in the forests close to Helsinki. Okay, so he's wandering the whole day through the forest. He cannot find his way. He's completely desperate, completely exhausted. At some point, he finds the rails, and he is happy that you know, hand car is passing by with a fin on it, and so he, you know, stops that guy and, you know, says, "How far to Helsinki?" "Well, to Helsinki, not very far. So can you take me with you?" Oh, so the Finnish guy agrees. So they, you know, they hop on, start pushing. So very enthusiastically, you know, 1 hour passes. A little bit less enthusiastically, 3 hours pass. 5 hours, 8 hours, right? So they push the car for 8 hours. the Russian guy is completely exhausted, so he cannot, push any further. So how far to Helsinki? To Helsinki? No, it's very far. Okay. Fluctuations. The preparation was longer than the joke, sorry for that. But it is a big moral, right? It has the hand car in it. So chapter 3. No. 3 will be fluctuations. And we will not have much time, so I just have basically 2 topics. I want to tell you a little bit about how this inflation actually gives you the right perturbations, basically. So we'll learn a little bit about QFT and curve space. But before we do that, I want to tell you, return back to CMB a little bit more and tell you some more stuff about CMB, which we'll do now and on Monday. So let's go back to CMB power spectrum. And just to remind you, we observe, if we are looking at different directions, we observe different temperatures. So we observe T as a function of the direction, if you want. And then you have these fluctuations in the temperature, which is T minus T0 over T0, where T0 is just the average temperature over the sky. So you basically average over all possible angles of T of n. Okay. And so these things are of order 10 to minus 5, so they are really teeny tiny fluctuations. And then this T0 is something like 3 Kelvin in average. Okay. So now you can expand these fluctuations in the spherical harmonics as we have done. So we have this thing sum over L and so these are the coefficients of the expansion which you measure. If you know the spectrum fluctuations, then this is what you measure. Just one thing, you know that delta T is of course real, but these guys, well, satisfy some nice conditions. So for imposing reality on this thing, it gives you that the coefficients of the expansion have to satisfy reality conditions. So delta T is real. That means that ALM complex conjugate has to be equal to -1 to power m and AL minus m. Okay. So everybody can believe that. So by the way, these spherical harmonics are very nice functions. They are orthogonal, they form complete set and everything. So it's just doing like a Fourier expansion, right? So now what you want to do is that you observe this power spectrum and you want to theoretically predict. So you want to make some prediction for the power spectrum and then you want to compare it to the observation. So want to find a theory and predict observed power spectrum so CL, that's exactly what I wrote last time, but now I'll put an index observed. This is what we observe. And that was defined by 2L plus 1. It was basically the length of ALMs for a given fixed L in this M space. So it's M minus L plus L ALM square. So this is what is observed and what gives you this very nice thing. Okay. And you choose this length, so you sum over M, because this is rotationally invariant. So if you actually rotate your universe, it doesn't matter. And the reason why this is rotationally invariant, and that's why people like it, so this is rotationally invariant. And comes simply from the fact that if you rotate your angle, I have some rotation acting on my direction. This is just a representation in this M space, dm prime for a fixed L. So this is a representation matrix of my rotation times epsilon Lm prime M. Okay, so for this reason, so this thing acts only, so for fixed L, this acts only on the M space. So if I choose this thing, which is the length doesn't change under the rotation in the M space. Okay, so that's why you choose this quantity to plot, because it's rotationally invariant. So it's a nice quantity to measure. So now comes the funny part. So let's make a framework is how the theory can predict this observation. And as I said, in some sense, the inflation gives you the right initial conditions for this theory, or it's the right theory to consider. So that's why it's so powerful. So if you want to create a theory for observing this guy, you simply say, well, let's consider an ensemble of possible universes. That's the first step, okay? Ensemble of possible universes. So now each of these universes is, characterized by some set of ALMs, okay? And then you have all these universes in the back, and then you pull one, and that has some specific ALMs, and you compare those ALMs to whatever you see here, whatever we observe in our universe. So randomly choose one universe which will be characterized by this one fixed ALM. But of course, if you want to talk about statistics of these things, you have to say, what is the probability that I choose this universe with this given ALMs? So this is this probability distribution given by P ALM. Okay. So some universes are more likely, some universes are less likely, given what these ALMs are. Okay, so ensemble of possible universes. So this is what you are doing. So they are building this framework, and you have to do it statistically, basically. Okay, so once you have these things, you may be asking, what are the various correlation functions between these ALMs? In particular, so this you may see something like it has two ALMs. It's like a 2-point correlation function in some sense, the CL. Okay, so you may be asking, what are the correlation functions, or what are the averages with respect to this probability? So then the correlation functions, or if you want probability averages, So for example, I put one ALM here, and then I put A, L prime, M prime, and so on. And then I do this probability average. Then this will be given by an integral over the measure. So the measure is, of course, a product of all possible ALMs. So it's a product of D ALM. So all possible ALMs. And then the probability also enters this measure. It's the probability of given ALM. And then I put whatever I have in my correlator, right? So then it's again ALM, AL prime, M prime, and whatever I want to calculate the average of. Right, so just the definition. Okay. So now, and then you want to compare, you know, these average things to whatever we observe over there. So, in order to be able to do this, I need to the theory has to predict what this probability is, because otherwise I cannot calculate these averages, right? So it's up to the theory to tell you what P is. Okay, and so what it is so for example, the inflation gives you sort of right kind of P, which you are to get out, but you have some observational constraints on this, what this P can be, observing whatever these things are. So P has to be rotational invariant. That's sort of a reasonable constraint. And the simplest possible P is the Gaussian P. And actually, there is no observational evidence for the fact that this probability is not Gaussian. So the simplest possible theory is you can think about Gaussian one. So what I mean by Gaussian is not as an exponential or something. Well, in some sense it is, but what you mean by that is that if you want to calculate, these various averages or correlation functions, you can use a Wick theorem, which you know from QFT. Which means that if I have, for example, a correlation function of odd number of things, it is automatically equal to 0. If I have of even number of things, then the total correlation function is given by the Wick theorem. Okay, so that means that all higher point correlation functions are given by the Wick theorem. Okay, so in particular, if I have A, and there's odd number of them, I have 0. If I have A1 to A4, then I do all possible contractions, or two-point contractions between these things. So I have A1, A2, A3, A4, and the other two combinations. So I have A1, A3, A2, and A4, and then A1 and A4, A2, A3. Okay, so that's an example how this works. So in order to characterize a Gaussian distribution, all you need to know is basically how the two-point function looks like. And then I can reduce everything to two-point functions. And as I said, so people playing with the fact that maybe this is not true, that maybe you need some non-Gaussianities. And this basically started after it was possible to calculate for the first time how these non-Gaussianities would look like and what the prediction would be. And that, believe it or not, actually is due to Maldacena. So it's his only cosmological paper. Otherwise, he's doing these ADS-CFT things, right? But he was the first one to actually nicely and compactly calculate what would happen if this probability were non-Gaussian. And you will do that calculation. It will take like 8 lectures probably in the exploration course. Okay, so that's something to look forward to. And you will have to learn many things on the way. So particularly, you will do this 3+1 splitting of GR. So basically, Hamiltonian formulation of GR. You will have to learn about in and out formalism in quantum field theory. You will have to do many things. Okay, but for us, let's just assume, because this is consistent with observation, that everything is Gaussian.
How is it consistent observation? Because didn't you say it's like the probability of different universes? How can you say, oh, we can see? It will be.
Okay, maybe it will become clear once I do one more calculation here. Okay, so let me do that calculation. So this is just an assumption, basically, if you want. I'm assuming that P is rotationally invariant, and then it's Gaussian. I'm just building a theory and seeing does it give me the observation or not. Okay, so if it is rotationally invariant, then if you do the average over a temperature which contains 1A, what is it equal to? It's both things actually give me the same result, rotational invariance and Gaussianity give me that this is equal to 0, exactly. So this thing must be true. However, if I have rotational invariance, I have this 2-point function, which is actually enough to say everything about my Gaussian distribution. So now I'm considering delta t at n and at n prime. So because this is rotationally invariant, it must be some function only of the angle between the two, right? So it must be some function over a scalar product of n and n prime. So it's a function of that angle. Okay, that's what rotational invariance gives me. And of course, you can expand this in the appropriate basis. Again, I am choosing like a complete basis, and I expand this guy in this basis. And so because this is something like cosine theta, it goes from -1 to 1, so I need a complete basis on -1 to 1. And that's the Legendre polynomials. So you expand this in the Legendre polynomial basis, and it goes like this, 2L plus 1 over 4 pi. And then the coefficients of expansion, which depend on this L. And for some reason, I choose this to call this CL. Okay, and then you have the Legendre polynomial, PL n of n prime. Okay. So by the way, this Legendre polynomial, okay, so this is my coefficients of expansion and tell me everything about what this guy is. But of course, this CL is not that CL, right? So that CL is something I observe. This CL is just a coefficient of expansion of this 2-point function. Okay. However, you can write this PL in terms of the spherical harmonics, 2L plus 1, sum over m, y, Lm, n, y, Lm star of n prime. And then you can compare whatever you have on the left-hand side. So I take this delta t, and for the delta t, I plug in that expansion, ALM, YLM. And then on the right-hand side, this is what you have. So from here, it follows that your 2-point function has the basic building block for your 2-point function is this one. ALM, A, L prime, and M prime. is delta L L prime delta M M prime CL. Okay, so this is what rotational invariance gives you. I'm just using the definition of what delta T is. The right-hand side has to be, well, I'm just choosing Legendre polynomials to expand my thing because it lives on -1, 1. And that CL is just a coefficient of expansion. And that CL gives you basically what is the basic block of your endpoint functions. Okay, so the CL is just, something, but that, represents everything that is to be known about my probability P, right? Because if I have this CL, I can calculate this two-point function. I postulated Gaussianity, so that's why I can everything reduce by Wick's theorem into two-point functions. I can calculate any point functions. And of course, any point functions give me what this probability is. Okay, so that's the theory. So now, of course, the question is, what is this CL has to do with our CL? Right? Why is it, again, CL? And the answer is that the average value of, well, okay, is the same thing. So want to relate CL observed and CL. Okay, so the first thing to calculate is the average. So I'm calculating whatever the average of the observed thing is. Well, by definition, CL observed is over there. So it's sum over, so it's 1 over 2L plus 1, sum over M, ALM star. Right, so that's from the definition of CL observed. So now 2L plus 1 is just a constant. I pull it out, and the average goes through the sum. So I have an average over this guy, which is delta L L. Okay, so this is equal to 1 over 2L plus 1 sum over M, ALM star ALM. This is delta LL delta MM CL. What is a minus 1? No, but that thing is the absolute value square. So it already has ALM star.
Yeah, but you want to use the relation of the expectation value of A.
Oh, so thank you so much for telling me. Very good. So this is actually one of them has to be star. Oh, thank you so much. You discovered a big mistake on the blackboard. Thank you so much. So yeah, so this is just that. And so it gives you that this is equal to CL. So on average, this CL is actually that CL. So that's why you can call it CL. Okay, so very good.
What are we doing average on the observational? Is that the average of the data or average over the probability distribution?
This will be the average over the probability distribution if you want. Okay. Well, so now a second thing you may be calculating is something like the variance. Is people are always interested in how different square behaves, and it's called cosmic variance.
When we define the observation one, should we use the observational value of the A?
Should we use what?
Like the observed value of the ALM.
Observed value of.
When we do the average,
Well, that's correct. Yes. So we are doing observed value of ALM. That's right. I'm saying that I'm cheating here. Can I go the other way around? Okay, let me think about it. Let me continue, and then let's return back to this. Okay, thanks. So variance is that you are doing now this guy, CL minus CL observed, divided by CL square. Now this is what it is. So if you calculate this guy, well, you have CL square over CL square is 1. So it's an average of 1 minus 2CL observed divided by CL. So maybe I'm doing exactly the other way around. Okay, let me continue and then let's think about this. CL observed square over CL square. Okay, so now as I define these guys, CL without observed is just a number, so I can always pull it out of this thing. And this guy I'll be averaging. So this is equal to 1 minus. Now the average of CL observed, we just established, is CL. Okay, so this is 1 minus 2, difficult mass. So it's minus 1 actually. And then this guy, so plus, 1 over CL square, and then this guy, CL observed square. So this is equal to minus 1 plus, now you have to plug in whatever the definition of CL observed is. So each of them has 1 over 2L plus 1, so you'll have 1 over 2L plus 1 square. CL square, 2L plus 1 square. And then you have sum over M and sum over M prime. And then you have ALM, ALM, ALM star. And then you have ALM prime, ALM prime star. Okay, so now you have to use your big theorem. Okay, so for example, I contract this guy and that guy, and then I contract this guy and that guy and this guy and that guy. So I get 3 terms. So I apply Wick on this thing. So now you're exactly right that I have to use this fact that for delta t real, I have this relation. So you will have some minus m's there and some minus 1 to power m. But you are lucky because you always have to do it twice. So that's why this minus 1 to power m actually never shows up. Do it yourself. And so what is this equal to? So this is equal to minus 1, and then we have 1 over CL square 2L plus 1 square. And then you have, as I said, 3 terms. So the first term is just, well, delta mm and delta m prime m prime. So you have delta mm, and there's a sum over m and m prime. And then you have delta mm, delta m prime, and then you have delta LL, but it doesn't do anything, so it's just delta LL. So that's the first term, and each of these averages gives you 1 CL, so you have now CL square. So that's the first term. Then you have the second term, which gives you delta m and then m prime, because I'm constructing now the first one and the third one. And it gives you these minus ones to power m, but they just cancel. So you have this guy is actually twice there, CL square. And the fact that there's no minuses, just do it yourself. And the last term is the same thing. I'm contracting the first term is the last one. So again, it will contract m and m prime. So delta m and m prime, delta m and m prime, CL square. Okay. So now delta mm and delta m prime doesn't really tell you anything in the sum, right? So it doesn't kill any terms of the sum. So this thing actually gives you, after the sum, is just 2l plus 1 square times CL square. This guy, however, tells you that one m prime is m. So it kills one of the sums. So only one sum is left. So this thing gives you 2l plus 1 times CL square. And this thing as well, 2l plus 1 times CL square. Okay? So we have, if you sum everything together, so we have minus 1 over CL square, 2l plus 1 square, and then in this bracket, it's these things here. And if you do it, you find that this is equal to 2l plus 1. So that's your variance in the average. So in other words, this variance gives you, like, so this is CL minus CL observed over CL square is square root of this, which is square root of 2l plus 1. So in some sense, if you want, the square root is typical for if you have n measurements, my mistake is square root of n. So that's why, so you have now sort of like 2l plus 1 measurements for given L. You have m goes minus L to L. So for given L, I have 2l plus 1 measurements. And so this is like square root of that. Okay. So now, however, this is very interesting from the point of view as you are looking at CL. Right? So this thing goes bigger and bigger as L is going smaller and smaller. So this is the origin of your error bars in the CL graph. So as your CL graph looks like something like this. So for small l, you have these large error bars. And they come from the fact that your universe happens only once. So there is no way to go around these error bars, because you simply will never have enough measurements. You have only one measurement. You only see the universe as it is, right? It doesn't happen many times. You cannot repeat the measurement. You cannot repeat the universe to measure, to get a new. So we have large error bars, large error bars for small l. Okay, and basically, it's an irreducible uncertainty what you can know about the structure of the universe. So universe happens only once. So now this is, completely exceptional thing in physics, right? So there's, as far as I know, there's no other discipline where you would have this fundamental constraint, right? Because you can always sort of repeat your measurement. You can always repeat experiments in the lab, but here you're experimenting on the universe, and that actually you cannot reduce. Well, yes, and in principle, if you travel, you would get some, true. But for the time being, you cannot get more information than this thing. So now, what is actually very interesting is that there are various theories which predict, modifications of this thing. And so, for example, loop quantum gravity, as we learned this summer predicts some modification of this spectrum based on quantum gravity effects. But the problem is that it exactly predicts the modification here for small l. So it's a nice prediction, but because of this cosmic variance, it's basically useless, right? Unfortunately for quantum gravity. So if you predicted, something new here, it'll be great, right? Because then you know your theory is right or wrong, because the measurements are very exact. But here they cannot be because of small l. So yeah. So let me finish here, and let's do polarization of CMB next week.